Okay, we are now recording. So again, we're working on a velocity graph and we're working through finding, like just making sure we can interpret what's going on. So the velocity, greatest velocity is going to be when the y value is the largest. The least velocity is going to be when the y value is the smallest. So J and O are positioned on that graph. When the velocity graph crosses the x-axis, the velocity is actually equal to 0. When the velocity is above the x-axis, the bat wing is moving in the forward direction. When the velocity is below the x-axis, the bat wing is moving in the negative direction. And so remember that, let's see, we've got speed is equal to the absolute value of velocity. So we got that piece in there. But then if we're working at question 4, when we start off, the velocity is positive, so we're accumulating distance. And then at point C, we stop moving. And then after point C, we start traveling backwards, so we're losing any distance that we gained. And so the total, or sorry, the greatest distance away from the starting position would happen at part C, but then the total distance is the greatest at I. So this would be the greatest total distance. And C is the greatest distance from the start value. So what questions do we have on 1 through 5 at this point? I should have asked you to type your story into the chat window so we could share that way. Does anyone want to read their story out loud? I guess you could raise your hand if you feel brave enough to share your story, or you could let us know in the chat window. Or if you want to go the anonymous route, you could type it in the chat window and then I could repost it to everybody. Okay. No one's, I'm not, if you're wanting to share your story, I'm not getting that information. Okay, awesome. Thank you, Kaisa.
Okay, could it be like if you like those helicopter toys that kind of like come down slowly? I'm imagining someone like threw one and they kind of like ran forwards, and that's the part like A to C, and then they kept kind of going back and backwards and then forwards again and then backwards as they're like watching it above them like kind of fall down to catch it.
So is the backwards and forwards, is that the person or is that the
Yeah.
drone thing? The
The
person.
person's on the ground running like as they're
Nice.
looking up
Cool.
to like see where it lands.
Yep. And so we can measure the distance from the starting point. Yeah, cool. Anyone else want to share? Okay, we got one in the chat window. Batman's flying forward and then starts to do a flip and flies backwards, and then another flip that is slowing down but starts hovering back and forth. Yep, anything where we've got this idea of back and forth motion. So yeah, the parallel parking, the overshooting, kind of backing up, anything along those lines. What other questions do you have about this activity? Do you feel like you have a slightly better understanding of how to like better practice at interpreting a velocity graph in terms of the physical world around us? That's kind of the point. Either that or I'm just like, let's put Legos in the lesson because Legos, because why not? Cool. Anything else? Any other questions? We have one request. Okay, yeah. Instantly takes off, slows down as he gets close, but the Joker snagged the plane and was dragging the bat plane away. Eventually, Batman breaks through the net and flies the rest of the way there. Cool. Good. Just this back and forth motion thing we've got going on here. If you really wanted to go crazy, you could work the acceleration idea into here. We didn't spend much time talking about that. So let's think about acceleration. The derivative of velocity is acceleration. So the slopes of the tangent lines would give us the acceleration. Where is the acceleration the greatest? And we might want to ask that question 2 different ways, because the acceleration that's marked on the graph right there, is that positive or negative? The place we've got acceleration marked on the graph, is that a positive acceleration or a negative acceleration? That's a negative acceleration, so we've actually got slowing down. So this would be the point where the batwing is slowing down the fastest. So it's like moving along and then starts to slow down. Or that's where the change in velocity is the greatest. And then come to a stop, and then you're kind of going the opposite direction there. So yeah, the rate of change is when the slope is the steepest in magnitude. The fastest acceleration in the positive direction would have to be somewhere like that tangent line, because that's where we have a positive slope. So yeah, the greatest acceleration is somewhere in this stretch. It's a little hard to tell maybe where it's exactly the steepest, but yeah, somewhere around EF, that stretch right there would be the greatest positive acceleration. So again, just reiterating, how can we interpret what's going on by using the ideas of derivatives and tangent slopes and things like that. Okay, if we wanted to talk more specifically about actually estimating what's going on with the graph like this, we could use something called a Riemann sum. So I don't know if we got to, again, I'm teaching and spelling just goes out the window some days. How many years have I been writing this word? So let's say that we have some sort of a function. We can actually keep the same function, and it's measuring the velocity. And we know that distance equals rate times time. So we have this multiplying relationship here. And if the rate is constant, then this computation is super easy. You just do the multiplication. But in this picture, the rate is not constant, it varies. Okay, it's changing. It starts off big, it gets negative, goes back to positive again. So when we have a variable quantity, then we need to use a calculus technique to do this computation. So if the rate is constant, so if we think about the rate as the how fast, if the how fast something is constant, then if we want to know how much of a thing we have, like how much distance, we just take the rate, the how fast, and we multiply by a change in time. So I might call this the how long. So you could think about that as like a delta t, and the how fast would be like a velocity or a derivative type of idea. And then how much would be like the original position. So if the rate is constant, how far you travel is simply the speed times how long you drove that speed, or the velocity times how long you maintained that velocity. And that's something you could do before calculus, but it's not a very exciting situation because we don't always drive on cruise control, right? Real life around us is pretty variable and flexible and changing. So if we have a multiplicative relationship, this idea that you take the how fast times the how long, and one of the quantities is variable, it changes. Sometimes you're going faster, slow down, speed up, that type of thing. Then you need to use calculus to do this computation. So this is the last third of calculus class. This is like your last big technique. The first one's limits, the second one's derivatives. Now we're into something called integration or integrals. Okay, and we'll work on defining this word integral over the next few days. But the idea is the integrals it's one strategy to undo a derivative. Okay, so we're working on the part of the class where we want to undo a derivative. If I give you the how fast, can you tell me the how much? And one way we started working on this is we started looking at an estimate. Okay, so this was on your quiz last time, where we might break this interval up into subintervals. We might say like x naught is equal to a, and then we'd have x1, x2, x3, x however many you have. And your last one is xn, and that's equal to b. And in this case, it'd be 5, since it's how many rectangles I drew, how many pieces I drew. Yeah, and so what we can do is we can say, well, why am I breaking this into subintervals? The idea behind subintervals is based off of couple ideas here. The first idea is that this statement I just wrote, if the rate is constant, then the computation is easy. If the rate of change is constant, the computation is easy. You just do the multiplication. So we say, okay, constant rate is good. It makes it easy. So what we're going to do is we're going to replace our variable rate with a constant rate. And so we could say, well, let's just assume that we move constant on the whole stretch. But that's a really bad approximation. So if we want to do better, we say, let's hold constant on these little stretches. Let's just pretend the speed is constant on these small stretches of the curve here. So what I'm doing is I'm replacing the variable equation with little segments of constantness. And this is actually called a step. You can think about this as a step function because we're like stepping from one value to another. So instead of the y values changing over the whole stretch, we're going to let the y values be constant for a bit, and then jump down to another value and hold constant, and then jump to another value and hold constant, and then jump to another value and hold constant, and then jump to another value and hold constant. Okay, so then on each of these stretches here, we have a constant rate, and so we can just use this multiplicative relationship straightforward, easy peasy. So in this example I've drawn here, this is my first interval, so I'm going to call this I equals 1, I guess, for the first interval. So the distance on the first interval is going to be the speed, so the velocity, which according to how I drew this picture, I went ahead and picked the velocity based off of, in this case, x naught. So it's going to be the velocity at x naught times delta t, or delta x. I suppose I should keep my variables consistent here. Let's do delta x. So this is where we take the velocity and multiply by a change in input. So are there questions on that relationship for that first little piece? And then I could do that for each of these intervals, each of these subintervals, and then just add them all together. And that gives me an approximation for the total distance traveled. So what questions do you have for me as at this point? Okay, and then the other thing is, notice that this velocity is corresponding to this vertical distance, and the delta x is corresponding to this horizontal distance. Yeah, this equation applies on the interval from x naught to x1, just this first little bit. We'd have to do a different equation to apply to that interval. Okay, so what happens when you take a vertical distance times a horizontal distance with geometry? What's another case where we multiply height times width? We get the area of a rectangle. So this is why we can kind of think about the distance as the area underneath the velocity curve. Okay, so we can think about the distance as the area underneath the velocity curve. And that kind of makes sense up here at the warm-up, like the peak distance, that was all distance where we're moving away from the starting point. The green distance is where we start coming back. And we can see that the pink area, the first pink area, is bigger than the green area. Yeah, so the basic structure of this estimation strategy is to replace your variable function with this step function where you have these little segments that are constant. So that's the first idea. Now we can dig in and get the nuance of when do you do an overestimate, when do you do an underestimate, when do you do a right sum, when do you do a left sum. And we may ask you to do an overestimate and underestimate. We may ask you to do a right-hand sum. We may ask you to do a left-hand sum. Okay, just looking from this first interval, is my estimation going to be larger than the exact value or smaller than the exact value? Do I have an overestimate or an underestimate just on this first interval from x0 to x1? It's an overestimate because this line is on top of the function. It's a little hard to see, but it would be really easy to see over here, right? This little triangle here, that's distance I'm adding in that we didn't actually travel. Okay, so if my constant rate is above the actual function, I'll have an overestimate. So yes, we want to talk about left, we want to talk about right, and we want to talk about improving the estimates. So what if we did like a trapezoid instead of a rectangle? That was a very awkward trapezoid. Let's try that again. That would be a more accurate shape, right? If we did a trapezoid, that would definitely be a more accurate shape. Another thing we could do is pick smaller rectangles, because each rectangle, the skinnier they are, the less error there is. There's a lot of ways to improve the estimation. Okay, So we decided this first rectangle actually is an overestimate. Is it a left-hand sum or a right-hand sum? And what do we mean by that? So is that first interval from x equals 0 to x equals 1, would that be a left-hand sum or a right-hand sum? And it's left-hand because if you take a look at the graph, this picture should be a little bit neater. Let me see if I can straighten that out a little bit, sorry. If you're sitting on the interval and you go right and you go up to the function, was that the representative height we used for this first rectangle? Or were we sitting on the interval going left and then going up to the function? Was that the representative height? Okay, so if you grab the left x value, the value that's on the left side of the interval, and plug that into the function to get the representative height, then you're dealing with a left-hand sum. So same thing for the second interval. The height corresponds to the function value at the left side. So that gives us a left-hand sum. So all the ones I drew from 0 to 5 are left-hand approximations. If we did a right-hand approximation, we'd go to the right side of the interval, plug that into the function, and that would be the height, the representative height. Okay, it's almost like it's an election. You have your jurisdiction here. You pick somebody in here to be the representative for the whole group. And in this case, for this picture, we picked the person standing at the left side there. And then we say their views or their values or their height represents the entire group. You could pick somebody in the middle if you wanted to and do kind of a midpoint approximation. So yeah, so there's a question in the chat window now about a generalization. Are left-hand sums overestimates and right-hand sums underestimates, at least for this equation? And that actually corresponds to if your function is above the x-axis and if your function is increasing or decreasing. If your function is decreasing, then a left-hand approximation will be an overestimate. If your function is decreasing, a right-hand approximation will be an underestimate. But if your function is increasing, if we had a different kind of function there, if your function were increasing, then the left is the underestimate and the right would be the overestimate. So you can make generalizations about overestimates and underestimates if you incorporate the increase or decrease. And if your function both increases and then decreases, then you kind of can't make those generalizations anymore. Wouldn't it be better to have a minimum estimate than a triangle that is the slope of a line between the right and left? So I don't know for sure that I'm understanding what's going on here, but I think I do. So I think maybe what you're saying is, could we draw a rectangle and then put a little triangle on top? Is that what's going on in the chat window? And this shape is actually called a trapezoid. And yes, there's such a thing as a trapezoidal rule for doing approximations. So you could do rectangles, you could do trapezoids, you can do any shape you want, really. And we'll talk about this. The trapezoid looks like it would be much better than just a rectangle. But we're gonna pull out some calculus tools to kind of avoid that question. We're gonna be a little sneaky there. Okay, so if I wanted to write a Riemann sum for this, I could do my second interval. And in fact, it's sometimes easier if you just go ahead and draw these rectangles in. See how bad my drawing is today, though. Holy cow. Those lines are straight, right? Yikes. Okay, and I'm just saying like I equals 3, this is the third rectangle, this is the fourth rectangle, this is the fifth rectangle, that type of thing. So the distance is going to be approximately equal to the velocity on the first rectangle times delta x plus the velocity on the second rectangle. And the velocity on the second rectangle comes from plugging in the left endpoint to get the height. So that's x sub 1 times delta x plus the velocity on the next rectangle times delta x plus the velocity on the next rectangle times delta x. And how many of these little rectangles do I need to have? Like, do I stop at x4 or do I go all the way to x5? Do I want to do one more or do I have enough? So let me know in the chat window, one more or enough? Do I need another rectangle? Good. Yeah, so it's not a bad idea to do a quick double check and say, well, I have 1, 2, 3, 4, 5 rectangles. I need 1, 2, 3, 4, 5 sums or 5 pieces to add in. Okay, so if I'm just going on this stretch, I'm not worried about the negative part of the graph. I'm just working on that stretch. I have enough rectangles there. Good. So how could I improve accuracy? I could improve accuracy by doing a different shape. So for example, a trapezoid, or I could do more rectangles. So the more subdivisions I do, the more accurate things are going to be. And in fact, it's easier mathematically just to get a bunch of rectangles than it is to actually do a trapezoid. So it's, I think you can streamline the process enough that you can use the theory to say like, yeah, we don't really care what shape we use as long as we use enough subintervals. But if you're doing an approximation on a computer, you might need to pay attention to the shape you're doing to get an optimal computational time. Maybe doing the computation for a trapezoid is faster on a computer than doing the computation of a rectangle. That's possible. So if you're in computer science, you'll spend some time worrying about optimization, although I believe that might be a little less important given how powerful computers are these days. But certainly in grad school, I had to take a computing class that helped us like, if you do your matrix multiplication this way, you're going to bog down your computer. But if you do it this way, it'll be faster. So these are all things to think about. How, like, especially when you want to get really accurate, you're going to want hundreds and hundreds or thousands and thousands of subintervals. You're putting this on a computer. You want to make sure that you're not just wasting computational processing power, which is still a hard thing to think about when our smartphones are so powerful. Do we really need to be careful if we have an unlimited supply of power? And the answer can be yes. Questions or comments at this point? Here's an example. Let's look at sine of x on the interval from 1 to 4. And let's do 3 rectangles. I might also call this n equals 3. Okay. And let's let sine be the velocity. We want to estimate distance. So we could do this with a graph, we could do it without a graph. One thing we're going to need to do is find, I think to get started, we want to find the x sub I values, and we want to find the delta x values. So here's a couple places to get started. So we could start by saying x naught. 0 is a good place to start counting, especially if you're in computer science. So what is my x naught going to be? It's going to be kind of the end point. Even if it's not the one we end up picking, it's x naught is the end point. So what is my x naught for this problem? Let me know in the chat window. What is x naught? And let's do a right sum. So if we take a look at the constraints for this problem, we're on the interval 1 to 4. So our x naught is going to be the leftmost interval, like the end point of the big interval. So x naught is going to be 1 in this case. Okay. What's the last x value? So like I called it x sub n up here. What is my x sub n value on this example? What would my x sub n be? Yeah, x sub n is going to be 4. So we could think about this one as x naught and this is xn. Now delta x is actually got a nice little formula. Delta x is b minus a over n. We also call this a to b when we generalize this problem. A is our left endpoint and b is our right endpoint. So that is the worst looking n. Try again. Okay, so b minus a over n, we do the, or you could do xn minus x naught, however you want to think about it. 4 minus 1 over 3, what's that equal? Oh no, I lied. We're changing this problem, sorry. Let's do 6 rectangles. Okay, so what is delta x? What's the value for delta x? In other words, how wide is each of my rectangles? Each of my rectangles is 0.5, or we could write it as a half, either way. Okay, so then, now that I have that, so I know that my big interval goes from 1 to 4, and if I'm taking that interval from 1 to 4 and I'm splitting it into 6 smaller intervals, I take the distance from 1 to 4 and I divide by the number of rectangles. So I get that each rectangle is a half wide. I know my first endpoint, the left endpoint of the first rectangle is 1. And the x sub i's are they're the endpoints of the subintervals, right? So x1 or x0, x1, x2, x3, x4, they're the endpoints of the subintervals. So I know x0. How do I find x1? Let me know in the chat window what x sub 1 is. Yeah, so x1 is going to be the previous value plus delta x. So it's going to be 1.5. What's x sub 2? It's the previous value plus delta x. So that's going to be 1.5 plus 0.5, or 2. What's x3? 2.5. x4 is 3. x5 is 3.5. And x sub 6 is 4. And I stop there because this is my x sub n. This is when I'm done. It's also the 4 for the endpoint there. So now that I have all my x values and I have my delta x, the sum is going to be sine of, wait, we're doing a right-hand sum. What's my first rectangle going to be? The first, like, what do I want to plug in for my first value? If I'm doing a right-hand sum, what's my first input? So, like, which x value do we pick to plug into the function to get the representative height? If I'm doing a right-hand sum, do I want to pick the left interval or the right interval? I want to pick the 1.5, yeah. And so actually, I want to pick these x values for a right-hand sum. I should probably do this over here, right-hand sum. And I would pick these x values for a left-hand sum. So that's kind of easy to maybe see how that would split out. So we do sine of 1.5 plus 1/2 plus sine of 2 times a half plus sine of 2.5 times a half plus sine of 3 times a half plus sine of 3.5 times a half. Do I need to also get the 4? I think I do. And then let's count. 1, 2, 3, 4, 5, 6 rectangles. That looks like that would be good. Okay, right early on I had a question in the chat window. Here you go. So if you wanted to condense this into summation notation, you could do the sum from I equals 1. Let's get my letters straight here. I equals 1 to 6, sine of x sub I. So then I'm doing like sine of x1 times a half plus sine of x2. And then that's corresponding to the x values that I need over there. Okay, so that's an approximation. That's the Riemann sum. It's an approximation. Now, what happens if I let n go to infinity? So here's a picture of a Riemann sum. Let's let the number of intervals increase. And do you see as the intervals increase, it looks like our approximate area is getting closer and closer to the exact area. It's 250, so if you have to leave, yeah. So if we go ahead and keep our delta x values fixed, but let n go to infinity, we're going to get the exact area. So if we take the limit as n approaches infinity of the Riemann sum, we get the exact area. And we're going to use this notation to describe exactly what we mean by the exact area. The exact value of the sum, once we let the thing go to infinity, is called a definite integral. So in this case, if we wanted the integral from 0 to 4 of sine of x dx, this is going to give us the exact area between sine of x and the x-axis on the interval from 0 to 4. Okay. And yeah, notice the return of the limit. So we started with limits this semester because we needed them to define derivatives, and we need them to define integrals, and integrals undo derivatives. So we're getting started at learning how to undo derivatives, but it's a kind of a tricky procedure. So it's going to take us several weeks to do that. I don't know what questions you have in the chat window. Obviously it's the end of class, so a definite integral can be interpreted geometrically as area. We can approximate the value using a Riemann sum. And if the area is like an exact geometric shape, we could compute this exactly. So that's where we're at. And we're going to spend the next few weeks digging into evaluating definite integrals and then learning about different kinds of integrals too.